13.3, the fundamental theorem of line integrals, video 6. I seem to have this pattern in this series of videos of starting one video by saying something about the previous one. I mentioned that the previous theorem was a biconditional with the correct conditions imposed on the domain, but I never mentioned the proof that path independence implies that the function is conservative, and hence the fundamental theorem of line integrals applies. But there's a nice proof of it on page 775 through 776. For those of you who are continuing in the theoretical math direction as opposed to physics or engineering, I highly recommend reading this proof and seeing if you can follow it. In upper level math classes, you will go from following proofs to deriving them on your own. And one strategy for learning how to prove things on your own is to read lots of other proofs to see techniques, ideas, inspirations, etc., etc., etc. So for those of you going down the pure math path, I strongly recommend trying to read the proof on page 775 and 776. I like to start concluding this series of videos by getting back to the original question about answering when are you a conservative vector field. Now, if you look closely at this theorem, we're starting out by assuming we have a conservative vector field, but as along the lines of what we've seen previously, we're going to follow up with, is this a biconditional, meaning does it work in both directions? But let's talk about this one first because it's easy to prove. If vector function f, or vector field f, is equal to pi plus qj, so p and q are your scalar component functions for I and j respectively. But if this is a conservative vector field, meaning that it's the gradient of something, and p and q have continuous first order partial derivatives on domain D. In other words, if we take the partial derivatives of p and q, they're continuous on some domain. Then the partial of p with respect to y is equal to the partial of q with respect to x. I actually alluded to this in a previous series of videos. I want to say it was in the videos for 13.1, but I don't recall off the top of my head. But the proof of this is fairly easy. I'm going to skip the part of the proof that requires the first order partial derivatives to be continuous. I'm sure it's an easy something, but it's not coming to me right now. And I'm going to try to write this proof as symbolically as possible with as few words as possible. F is conservative implies, and here's a symbol you may not have seen before. It's a backwards capital E. It is a symbol for the phrase there exists. There exists a function f. And here's another symbol you may have not seen before. It's a backwards lowercase epsilon. It's a symbol for the phrase such that there exists a function f such that the gradient of lowercase f is equal to capital F as a vector function. That's what it means to be conservative. And this implies that, and remember how you take the gradient of a function, you take the partial derivative to get the I component function, and the partial with, let me try that again. You take the partial derivative of the potential to get the with respect to x, to get the I component function, and you take the partial derivative of the potential function with respect to y to get the j component function. So this implies that p is equal to the partial of derivative of lowercase f with respect to x, and q is equal to the partial derivative of f with respect to y, because we're assuming that this is equal to the gradient of that. But what does this imply? This implies that if I take the partial derivative of this first equation on both sides with respect to y, the partial derivative of p with respect to y is the partial derivative of f with respect to x with respect to y. And if I do the same thing over here, except take the partial derivative with respect to x on both sides, then the partial derivative of q with respect to x is equal to the partial derivative of f with respect to y with respect to x. But there was a theorem way back when you first started talking about partial derivatives that said mixed partial derivatives were equal. It was called Clairaut's theorem. Some French mathematician, I can tell because it's got all the letters at the end that you don't say. You know, French language is a pretty one, but they sure waste a lot of vowels and consonants at the end of their words. Back on page 637, that was banter stalling while I looked in the index. Back on page 637, and this will explain why the condition on the first partial derivatives is required. I'm not going to write it on the board, but on page 637, we had a theorem that says, suppose a function lowercase f is defined on a disk D that contains a point. Suppose the mixed partials are both continuous on D. So that's why we need a continuity to refer to Clairaut's theorem on page 637. But there was a previous theorem that said mixed partial derivatives are equal under the correct conditions, and this gives us the correct conditions. These are mixed partials, they're equal, therefore the partial of p with respect to y is equal to the partial of q with respect to x. So it's a direct consequence of mixed partial derivatives being equal. But is this really what we need? What we need is something that concludes with then f is conservative. We don't need something that starts with is f, if f is conservative, we want to conclude f is conservative. So we have this nice conditional, but it's not in the correct order that we want to draw this conclusion. Can we just turn it around? If this, under the right conditions, then this? Well, you can't always just reverse a conditional. And by the way, when you reverse a conditional, you get what's called the converse. I noticed that the author referred to the converse as the converse. For example, if I live in Tyler, then I live in Texas. The converse of that would be if I live in Texas, then I live in Tyler. From a logic perspective, if a conditional is true, it doesn't imply that its converse is true, and it certainly doesn't imply that the biconditional is true in both directions. But it's always a good question to ask, is it true in this particular case? So asking, is this a biconditional, is like asking, is the converse true? If these are equal, then can we conclude that the original function was conservative? And just like in the previous video, the answer is almost. What do I mean by almost? Well, we have to impose a few more conditions on the domain in order to get the reverse equivalency, the reverse implication, and therefore establish an equivalency. So what conditions do we need to impose on the domain? Well, not only must it be open and connected, it must be open and simply connected. If the domain D is open, and again, what that meant, loosely speaking, is it doesn't contain any points on its boundary, but more specifically, it means if you pick any point on its interior, you can locate a disk that contains that point, and the entire disk is contained inside the set without crossing the boundary. But if the domain D is open and simply connected. Now, simply connected is not the same as connected. Connected means if you pick any 2 points, you can connect them with a path that doesn't leave the set. Simply connected means, I know how to say it, I just want to see if there's a more intuitive way to say it. Simply connected not only refers to paths, but closed paths. So simply connected means connected. So any 2 points can be connected with a path that is contained in the set, and every closed path only contains points in D. And you might be thinking, well, wait a minute, if it contains every path from point A to point B, how could every closed path possibly not contain points in D? Well, I'll show you. Guess we don't need this proof anymore. I mainly wrote that proof to show you how to prove things symbolically, but before you go doing that, make sure you know what all the symbols mean and how you can use them correctly. So what do I mean by simply connected? Well, here's an example of a domain that is not simply connected. Domain D. Let's puncture it by cutting a hole out of the middle. So kind of like a warped donut, if you will. As long as we don't include the boundary, and that's what the dashed line usually indicates. For a solid line, that means that you're including the boundary. And by the way, any set that contains all of its boundary is called a closed set. There's more to it than that, but for our purposes it will suffice. This set is open. No matter where I pick a die, I can find a small enough closed disk that's contained inside of that donut. It is connected, meaning if I pick any 2 points inside of here, I can connect them with a path that doesn't leave the set. But it's not simply connected. To be simply connected means that if I form any closed path inside, then basically everything on its interior is also in the set D. In this case, every point in the interior of this closed path is contained in set D, but I can draw a closed path whose interior contains points that are not in set D, as long as that closed path includes the hole in the middle of the donut. That closed path does not contain points that exclusively belong to the domain. It also includes all these points in this hole. So that's an example of a domain that is open, fails to contain its boundary. Connected, you can get from point A to point B without leaving the set, but not simply connected because there exists a closed path whose interior contains points that don't belong to the domain. So basically what this, I want to say hypothesis, that's not the word I'm looking for, this antecedent of this conditional, that's the if part of an if-then. You can also call it the hypothesis. The hypothesis of this conditional says your domain can't have any holes in it. So if D is open and simply connected, so let me erase all this now. Open, connected, and simply connected. I want to say that simply connected implies connected, but I'm a little rusty on my topology. Okay, so here's the other direction. If D is open and simply connected, and vector function f equals pi plus qj, so p and q are the component functions of I and j respectively, have continuous first order, just meaning first derivatives, partial derivatives, and my apologies, I left off an important thing in here, and P and Q, so we're talking about the component functions. All right, so D is open and simply connected, doesn't contain its boundary, you can connect any 2 dots, but there are no holes in the domain. And vector function f equals pi plus qj, and p and q have continuous first order partial derivatives defined on D. There's a lot of ifs here. Big hypothesis. And there's another. And py equals qx. So finally, we're stating in the hypothesis here the conclusion of this previous conditional. All right, so we can go ahead and set up the then. We're finally going to get to the conclusion of this conditional. All right, so if your domain is open and simply connected, doesn't contain its boundary, you can connect any two dots without leaving the set, but the domain has no holes in it. And vector function f is pi plus qj, and p and q have continuous first order partial derivatives on d, and the partial of p with respect to y is equal to the partial of q with respect to x. So a lot of things have to be in place. Then f is conservative. So this theorem is almost a biconditional, meaning that you can read it in both directions. This whole mess here is actually Theorem 6, and both of these theorems can be found on page 777. It's a lot to say just to, draw the conclusion f is conservative, but let's just summarize it nicely. If your domain doesn't have any problems and doesn't contain its boundary, I'll be even more specific. If your domain doesn't contain its boundary and doesn't contain any holes, and this is true, then your function is conservative. So, and we kind of actually did that once upon a time, but assuming that your domain doesn't have any problems, then being conservative is equivalent to saying this. What happens if your domain has problems? We'll take some more advanced math classes and you will find out. All right, in the next video, we're going to answer the questions, are these conservative? And when the answer is yes, we're going to attempt to locate the potential function, the function whose gradient gives us the vector function, and then I think we'll be done. Oh, that was a long video. Sorry about that.